Welcome back to the deep dive. Today we are moving past, the macroscopic beauty of the world and descending into the microscopic realm, really the geometric heart of solid matter.
Hmm.
We are embarking on a deep, systematic exploration of Chapter 8, Symmetry in Crystallography.
And this is a big one.
It really is. If you think of crystallography as, I guess, the architecture of the universe, then symmetry is the foundational math that writes the building codes.
That's a great way to put it.
When we talk about symmetry outside of science, it's often linked to aesthetics, like a balanced garden, a visually pleasing design. But in this field, symmetry is mathematical law.
Right. It's the constraint that determines how matter organizes itself. It's really the difference between beauty as we perceive it and beauty as pure, unyielding structure.
Absolutely.
That's why we started our prep with that quote from Bertrand Russell, because it speaks directly to this idea of crystalline perfection. He said, "Mathematics, rightly viewed, possesses not only truth, but supreme beauty."
A beauty cold and austere like that of a sculpture.
It's exactly. Sublimely pure and capable of stern perfection. And that phrase, stern perfection, that's what we're talking about today.
That quote is our guiding light, really. This deep dive is our mission to unpack that stern perfection. We're going to systematically move through the theory of symmetry transformations in space.
And we'll start with simple objects and the linear algebra that defines their movement.
And then build all the way up to the highly constrained world of repeating crystal lattices.
We will cover the nuts and bolts, the matrices that define rotation, the need for 4D homogeneous coordinates to handle translation, and, most importantly,
The big one.
the profound geometric constraints that limit the infinite possibilities of spatial movement down to the finite reality of crystal structures.
Let's unpack this. So section 8.1, we begin with the most fundamental concept. The symmetry is just an arbitrary object. Before we even bring periodicity into the mix, what makes something symmetric in a mathematical sense?
The definition hinges on one key idea.
Yeah.
Self-coincidence. An object is symmetric if, after a specific action, be it a rotation, a reflection, or a displacement, the resulting arrangement superimposes exactly upon itself.
Okay, so it has to land perfectly on its own footprint.
Perfectly. And crucially, the transformation has to ensure that the distances between all internal points of the object remain unchanged. There's no stretching, no warping. It has to be a rigid body motion.
So a symmetry operation is the action itself, that transformation, or I guess a combination of transformations, that achieves that self-coincidence. It's the verifiable proof that the symmetry exists.
Precisely. And here's a foundational nugget that's easy to miss. Every single object, regardless of how asymmetric it appears, possesses at least one symmetry property.
Which is?
The identity operator. It's the operation of doing absolutely nothing.
Right.
It brings the object into self-coincidence immediately, which makes it a required element of every single symmetry group.
And to navigate these operations, we need a common language. That's where the notation systems come in and, well, there's often confusion between the two primary standards.
That's right. We use two main systems, and it really depends on the field. The international notation, which is also called Hermann-Mauguin, is the professional standard for crystallographers. It uses numbers and letters like M for a mirror or N for a rotation. It's very descriptive of the symmetry elements.
And then there's the Schoenflies notation. That's the one you see more from physicists and chemists, especially in molecular and quantum contexts.
Exactly. Schoenflies uses symbols like Cn for a rotation and sigma for a mirror. We are going to prioritize the Hermann-Mauguin symbols because that's the standard in this field, but we'll continuously reference the Schoenflies equivalent just for context.
Okay, good. So let's move to the algebra that underpins all of this.
Right.
Rotation. The chapter uses a really simple, compelling visual aid. A regular hexagon centered at the origin of a 2D Cartesian plane.
Yeah, the hexagon is perfect because it forces us to quantify the movement. If you pick a point P with coordinates, x, y, and you rotate it counterclockwise by an angle theta, it lands at a new position, P prime, with new coordinates, x, y.
So the question is, what's the systematic rule that maps xy to xy?
Exactly. And this is what we call the coordinate transformation, or the passive interpretation. The object moves, but the reference axes, the x and y axes, they stay fixed.
Okay.
When you trace the geometry of that point and use the trigonometric addition theorems, you find that x and u are just linear combinations of the original x and y and the trig functions of theta.
And when we write that linear combination using linear algebra, we get the fundamental 2D rotation matrix d theta.
Yep, the matrix with cosine theta minus sine theta on the top row and sine theta cosine theta on the bottom.
And that matrix is the complete recipe for rotation in a plane.
It is. And if we want to transition this idea to 3D, say for a rotation around the z-axis, the matrix just expands to a 3 by 3. We simply ensure that the z-coordinate remains completely unchanged.
So the third row and column are just 0, 0, 1.
Exactly, 0, 0, 1, and its transpose, which keeps that original 2 by 2 rotation block in the upper left. And this mathematical extension is crucial because, well, crystals exist in 3D space.
That matrix is fascinating because it's not just any algebraic construct. It's constrained by the physical world. Since a rotation can't stretch or compress the object, the matrix itself has to have specific properties.
It does. The constraints are the essence of what we call isometry. First and foremost, rotation matrices, the D matrices, are orthonormal.
Orthonormal, what does that mean conceptually?
It means that if you multiply the matrix by its transpose, you get the identity matrix. Conceptually, orthonormality is the mathematical guarantee that the rotation preserves both distances and angles within the object.
So the length of the vector stays the same after the transformation.
Exactly. The vector magnitude is preserved. If a matrix failed this test, the rotation would deform the shape, and that's forbidden in a symmetry operation.
And there are other properties too.
Yes. The other two critical properties deal with orientation and, well, efficiency. The determinant of any proper rotation matrix is always equal to +1.
Always +1.
Always. This is the key mathematical identifier that tells you the transformation has maintained the handedness of the coordinate system. It hasn't reflected or inverted the object.
And finally, the inverse.
The third property, which is computationally wonderful, is that the inverse of a rotation matrix is simply equal to its transpose.
Which is much easier to calculate.
Oh, way easier. Finding an inverse can be tedious, but finding the transpose is trivial. This elegant relationship makes working with sequential rotations highly efficient. The whole system is a self-contained unit of that stern perfection, built to model movement without distortion.
Now, here is a point that often trips people up, and we need to clarify it precisely. This duality between coordinate transformation and basis vector transformation. The physical movement is identical, but the math changes depending on your viewpoint.
Okay, think of it this way. Imagine you have a car and a map.
Okay, the car is the object, and the map is our reference frame.
Right. When we used the rotation matrix d theta to find the new coordinates, we were using the coordinate transformation, or what we call the passive interpretation.
We kept the map fixed and tracked the movement of the car as it drove.
Precisely. The car's coordinates changed, but the basis vectors, the north, east, up directions on the map, they did not.
So now let's flip that. What if the car, the object, is fixed in space?
If the object is fixed, but we want to describe its location relative to a moving frame of reference, the active interpretation, then we have to rotate the basis vectors themselves. And to do that, the mathematical relationship flips.
How so?
You have to use the inverse, or in this case, the transpose, of the original rotation matrix, d theta.
So you use d to transform the coordinates relative to fixed axes, and you use its transpose, d transpose, to transform the axes themselves relative to a fixed object.
Precisely. The overall geometry is the same, but the math changes based on whether you are tracking the components or transforming the frame. For crystallography, especially with the site symbols we'll get to, the passive or coordinate approach is generally the preferred convention. We move the crystal within a fixed unit cell frame.
Okay, let's complete our set of pure arbitrary operations with the mirror operation. This introduces the concept of an improper motion. Let's consider a mirror plane that coincides with the YZ plane.
Right. So when you reflect across the YZ plane, the Y and Z coordinates don't change, they're invariant, but the X coordinate gets flipped across the 0 point. So X moves to mass X. This is a fundamental change in orientation.
And we can write this in a very clean 3 by 3 transformation matrix, which is almost the identity matrix.
It is. It's just
Sure.
manic 1, 0, 0 in the first row, then 0, 1, 0, and 0, 1, 1. That single -1 on the diagonal is the mathematical representation of the reflection.
And if the mirror were perpendicular to the axis, that -1 would just move to the middle position.
Exactly. And this simple flip of a sign tells us something critical. If you calculate the determinant of this matrix, it's -1. And that is the mathematical signal that we have performed an improper motion, one that changes the handedness of the coordinate system.
Okay, so now we move into section 8.2, where we formalize these different types of operations and critically introduce the strict rules imposed by crystal structures.
Right, and we should just reinforce the active versus passive view one last time. As we said, the active operator acts on the object's points, moving the object while the reference frame is fixed.
And the passive operator acts on the reference frame itself.
Right. And while they're both mathematically equivalent through the matrix inverse, from here on out, we're going to use the active approach. We're visualizing the structure moving relative to the fixed XYZ axes of the unit cell.
Got it. So we established that we only deal with isometric transformations, those that preserve distance and angle, but we need to formalize the difference in their physical reality.
The defining split is based on handedness. Transformations of the first kind, or proper motions, include pure translation and pure rotation.
These are things you can physically do.
You can physically realize them. If you had a model of the object, you could pick it up, move it, and rotate it into its new position. They preserve handedness. A left hand remains a left hand, and the determinant of their rotation matrix is always +1.
And the transformations of the second kind, the improper motions.
These include reflection, inversion, and combinations involving them. They cannot be physically realized without sort of passing through a mirrored state. They fundamentally change the object's handedness.
A left hand becomes a right hand.
Exactly. They require a flip, and their rotation matrix component always has a determinant of -1. This distinction is really the bedrock of understanding how all these symmetry operations are classified.
And this is where we cross the threshold from pure geometry into crystallography. We introduce the constraint of translational periodicity.
A big one.
In a crystal, the structure must repeat infinitely in space, governed by the lattice translation vector T. This requirement acts like the ultimate geometric censor, vetoing most of the symmetry operations that are allowed in arbitrary objects.
This is arguably the most elegant piece of geometry in the whole chapter. I mean, imagine you're trying to tile an infinite floor using perfect, identical geometric shapes.
Okay.
Squares work, triangles work, hexagons work, but as soon as you try a pentagon of 5-fold rotation, you realize you can't fill the plane without introducing gaps or overlaps.
Right, it just doesn't work.
It doesn't. So the constraint of tiling space perfectly dictates the allowable rotational angles.
This visual constraint translates into the famous rotation rule, the 5-fold constraint. Only 1, 2, 3, 4, and 6-fold rotational symmetries are permitted in crystals. But the key is proving why this is true mathematically.
And the proof is so powerful because it uses very little information. You take two adjacent lattice points, A and B, separated by the lattice translation vector 2. Now, if we apply a rotation of angle alpha around an axis, the points move to A' and B'. For the lattice to remain periodic, A' and B' must also be separated by a vector that is an integer multiple of the original translation vector.
So the new vector, T' has to equal m times t, where m is some integer.
Exactly. And using some vector analysis and trigonometry on the resulting geometry, you can derive a really clean relationship linking that angle alpha to the integer m,
Which is
the foundational equation. Cosine of alpha equals 1 meter 2.
And that tiny equation is the master key to crystallographic symmetry.
It is, because the cosine of any angle has to fall strictly between -1 and +1. This immediately limits the possible integer values for m.
So we can just test them.
We can test them explicitly. So if m3 cosine alpha is -1, that's an angle of 180 degrees, which is our 2-fold rotation.
Right.
If m2 cosine alpha is -1/2, that's 120 degrees, our 3-fold rotation.
If m1 cosine is 0, so 90 degrees, a 4-fold.
If m is 0, cosine is 1/2, 60 degrees, a 6-fold.
And if m is -1, cosine is 1, which is 360 degrees, or just a 1-fold rotation, doing nothing.
And anything else, like m4, gives you a cosine less than -1, which is impossible.
So the 5 allowed rotations, 1, 2, 3, 4, 6, are not arbitrary preferences. They're the only 5 rotations possible that allow a crystal to repeat itself without gaps or inconsistencies.
That is truly stunning. It's the ultimate example of how mathematics dictates physical reality in material science. Any rotation order outside of this, most famously the 5-fold rotation, is physically incompatible with the fundamental concept of an infinitely repeating lattice.
Okay, so now that we know our restricted toolkit, let's look at how we symbolize and represent these operations, starting with pure rotations of order n.
So a rotation is defined by the angle 2p pi and around the rotation axis. We use n in Hermann-Mauguin or Sheenen in Schoenflies. The diagrams that crystallographers use, these stereographic projections, they show these rotations using specific graphical symbols.
Right, if you look at the projections, you see that a two-fold axis is represented by an ellipse or a lozenge.
A threefold is a triangle.
A four-fold is a square, and a six-fold is a hexagon. These symbols are absolutely essential for reading any crystal structure diagram. They tell you exactly which symmetry axis is present and where it is.
And we can easily write their 3x3 transformation matrices. For example, a two-fold rotation, 180 degrees, around z requires cosine of 180, which is -1, and sine of 180, which is 0.
So the resulting matrix is just -1, one along the diagonal. Very simple.
Very simple. A threefold rotation, 120 degrees, has more complex fractions, -1/2 and square root of 3/2, but the underlying rule is always the same.
Now, the moment we introduce pure translation, a simple displacement by a vector t, we run into a serious mathematical roadblock. Why can't we use our neat 3x3 matrix system for translation?
Well, our 3x3 rotation matrix, D, operates on a 3x1 position vector R to give a new position R as doctor. This kind of multiplication requires that the origin, 0, 0, 0, transforms to the origin, 0, 0, 0.
And a pure translation fundamentally violates that rule, unless the translation vector TO is 0. Translation moves every point, including the origin.
Exactly. So to solve this, we need a mathematical loophole, really, that allows us to incorporate addition, which is translation, into a framework designed for multiplication, which is rotation. The solution is the use of homogeneous coordinates.
We jump up a dimension.
We do. We move from 3D space to a 4D representation. A 3D point by 1 by 2 by 3 is now represented by the 4D vector by 1 by 2 by 3, 1. We just tack the number 1 onto the end.
And that lets us define the 4x4 transformation matrix, the site symbol, WAVT. And this unified matrix can represent both rotation and translation at the same time.
Yeah, let's visualize this W matrix. It's a 4x4 block matrix. The entire upper left 3x3 block holds our rotation matrix D.
Which is the identity matrix for a pure translation.
Right, and the key is the top right 3x1 column vector. This is where the translation components T1, T2, T3 live, and the bottom row is always fixed as 0, 0, 0, no 1.
So when you multiply the 4D position vector by this W matrix, the rotation happens in the top 3 rows, and the translation components are simultaneously added to the X, Y, Z positions because of that 1 in the 4th position to the coordinate vector.
It's an incredibly elegant mathematical device. It unifies every single space symmetry operation, from a pure rotation to a complex screw axis, into a single, consistent algebraic framework.
Shifting back to improper motions, let's revisit reflection, M or sigma. We already saw that the mirror matrix has a determinant of -1. Physically, this operation is defined by the mirror plane.
Right, and if we look at the stereographic projection diagrams, reflection is crucial. A mirror plane is typically a solid line. If you start with a point above the plane, say an open circle for the northern hemisphere, the reflection takes it to the southern hemisphere, a closed circle. This jump across the plane is that spatial flip that changes the handedness.
And the other fundamental improper motion is inversion, overline, or I.
Inversion is a point operation centered at the origin that maps every point R to SR. It's equivalent to rotating by 180 degrees and then reflecting through a plane perpendicular to the rotation axis.
And it dramatically changes the handedness. Mathematically, how does the inversion operator look in the seat's symbol framework?
It's WE0. The D matrix is the negative identity matrix, E.
So -1 runs down the diagonal.
Exactly. And when this matrix multiplies the position vector, it flips the sign of X, Y, and Z simultaneously, projecting the point through the origin. And since it's a point operation, the translation vector T is 0.
So far, we've been assuming that all these rotation axes and inversion centers pass through the origin. But in real space, symmetry elements are everywhere. How do we handle an operation that occurs around an axis that's not passing through 0, 0, 0?
No. We use the power of the site symbol and a specific decomposition technique. So imagine a rotation axis parallel to the z-axis, but displaced to a location defined by some vector r.
So this complex operation, W, can be broken down into 3 simpler sequential transformations.
That's the elegant solution. We define the overall transformation W as a product of 3 matrices, W1, W2, W3.
Okay, what are they?
So W3 is a translation of the entire system by the vector RR. This moves the point of interest and the rotation axis to the origin.
Step 1, move to the origin.
Step 2, W2, perform the pure rotation d theta around the now centered origin. This is a simple rotation matrix D0.
And then step 3, W1.
Translate the system back by plus R.
So we've effectively used 2 pure translations and 1 pure rotation, all easily represented by 4x4 matrices, to describe a single, more complex transformation far from the origin.
And this mathematical maneuver ensures that every single symmetry operation that exists in a crystal, regardless of its position in the unit cell, can be quantified and analyzed using the algebraic rigor of this 4x4 matrix system.
Now we get into the most complex and structurally defining operations, combinations.
Right.
These combinations are what generate the 230 possible space groups.
Yes. The first combination involves 2 improper operations. Roto-inversion, symbolized by overline in Hermann-Mauguin. This combines an n-fold rotation axis with an inversion center located on the axis.
Let's focus on the 3-fold roto-inversion overline, which is crucial in trigonal and hexagonal systems.
Okay, so overline means you rotate by 120 degrees and then you invert through the origin. If you trace a point, the first operation moves it 120 degrees and flips it to the opposite side of the center.
And the second operation
Moves it another 120 degrees and flips it back up. After 6 steps, the point returns to its starting location. This single operation generates 6 equivalent positions, establishing a high degree of symmetry instantly.
And there are critical equivalencies here that simplify the notation.
Yes. For example, the 2-fold roto-inversion, overline, is mathematically identical to a simple mirror plane.
Oh, really?
Yeah, imagine rotating 180 degrees and then inverting through a point on that axis. Geometrically, that's precisely the same as reflecting across a perpendicular plane. We also find that the overline roto-inversion is equivalent to a 3-fold rotation axis with a perpendicular mirror plane.
So crystallographers prefer the roto-inversion symbol because it's more compact.
Exactly. It provides a single symbol for these combined improper motions.
The other type of combined improper motion is mirror rotation, symbolized as tilde or SN in Schoenflies. This combines an n-fold rotation axis with a mirror plane perpendicular to that axis.
Right, and the relationship between roto-inversion overline and mirror rotation SN is what makes the notation confusing for newcomers. As we just said, for even orders, they're equivalent. So overline 4 is equivalent to S4.
But when the order n is odd, the relationship changes significantly.
It does. For an odd n, the mirror rotation tilde is equivalent to a roto-inversion of order 2n, or overline. For instance, S3 is equivalent to overline.
Oh, okay.
And this complexity is a major reason why the Hermann-Mauguin system, the one we're focusing on, just prefers the roto-inversion notation. It reduces the number of primary symbols you have to learn.
It's a great example of how symmetry is often redundant, and the choice of which primary symbol to use is just a matter of convention, not some absolute mathematical truth.
Exactly.
Okay, let's introduce translation back into the rotation framework with the screw axis. This is the simultaneous combination of an allowed rotation and a translation that is parallel to the rotation axis.
Screw axes are essential for space groups because they generate the helical, winding structures you often see in complex materials. The crucial constraint for crystalline periodicity is that the translation T must be a specific fractional portion of the lattice vector along that axis.
That fraction is defined by T(m)T0, where n is the order of rotation 2, 3, 4, or 6 nm, is an integer from 1 up to n1.
And we symbolize this using nm. That subscript m tells you the number of full rotations required before the translation component completes a full lattice vector.
So let's visualize the difference using the 6-fold family. We have 61, 62, 63, 64, 65.
Okay, consider 61. That's a 60-degree rotation and a 16 translation. After one full rotation, so 6 steps, the point has translated exactly 16, which is just 2d0. It lands on an equivalent lattice point.
Okay, now compare that to 62.
So 62 involves a 60-degree rotation and a 26 or 13 translation. It only takes 3 steps to get to 180 degrees, and 6 steps to translate 6, 26 is 0, which is 2 times 0.
Ah, so the total translation distance after n steps is the pitch. The 62 screw axis generates points that are further apart helically than the 61 axis.
Exactly. And furthermore, we have to note the concept of enantiomorphism. The NM and NNM screw axes are non-superimposable mirror images of each other.
One is right-handed, the other's left-handed.
Yes. So 61 is the mirror image of 65. They are fundamentally distinct symmetry operations. The presence of one versus the other actually defines the chirality of the resulting crystal structure.
And this complexity is seamlessly handled by the site symbol W as EDT. We just insert the rotational D matrix and a fractional translation T side by side.
And the final combined operation is the glide plane. This combines a mirror reflection with a translation vector T that is parallel to the mirror plane.
The rule is stringent. The translation vector t must be half of a lattice translation vector. This is what distinguishes a true glide plane from just a mirror operation happening off-center.
And the physical consequence of that half translation is critical. If you apply a mirror operation twice, the object returns to its original position.
Right.
But if you apply a glide operation twice, the point is translated by 2, t2, which equals t. This results in a pure lattice translation, which demonstrates its compatibility with the periodicity.
The chapter outlines 4 types of glide planes, based on the direction and magnitude of that half translation.
First, you have the axial glides, A, B, and C. These glides translate the point exactly halfway along the corresponding lattice axis, A2, B2, or C2.
Okay, then the diagonal glide, N.
Right, this involves a translation that is half of a face diagonal, something like A plus B2.
And finally, the most geometrically constrained type, the diamond glide, or D. This glide plane translates the point by only a quarter of the face diagonal, like A plus B4. Why only 1/4? That magnitude seems non-intuitive compared to the half translations of the other glides.
That's the subtlety of the diamond structure. The D glide only appears in specific, highly coordinated structures like the diamond cubic lattice. For the operation to close and maintain the periodicity of that complex lattice, applying the D glide 4 times must result in a full lattice translation.
That's it.
Since the operation includes a reflection and a translation of 14 of the diagonal, 4 steps combine to yield a total translation equivalent to a full face-center translation. If the translation were 12 the diagonal, the structure would be unstable or incompatible. The 14 fraction is forced by the geometry of the structure itself.
That makes the D glide a perfect example of how the geometry of the crystal structure dictates the mathematical possibilities of its symmetry elements.
And just like the screw axis, the matrix for a glide plane is a 4x4 site symbol. WDT is WDT. The D matrix is the mirror reflection matrix, so determinant -1, and the TED vector contains the specific fractional translation.
Okay, we've built up all the components. Now let's tie the mathematics back to classification and the final structural constraints.
Right, so we established earlier that the determinant is the mathematical discriminator between proper and improper motion. This is a crucial concept.
If the determinant of the 3x3 rotational component matrix D is +1, the operation is of the first kind. It's a proper motion, it preserves handedness.
Which covers all pure rotations, translations, and screw axes.
And if the determinant of D is -1, the operation is of the second kind, an improper motion.
This covers reflections, inversions, roto-inversions, and glide planes. The coordinate system has been flipped.
This rule is powerful because it allows us to instantly classify complex composite operations.
Absolutely. If you combine multiple operators, the determinant of the composite matrix C is simply determined by the number of second-kind operators involved. Let's call it Q. The rule is DC mod is 1Q.
So if you combine 2 improper operations, like a reflection then an inversion, Q is 2, the determinant is +1. The composite operation is proper.
Exactly. It does not change the overall handedness. If you use one improper operator, Q is 1, the result is improper. This rule is essential for tracking chirality in crystal structures.
Now let's define point symmetry. We get a point symmetry operation by ignoring all the translations, right? Setting T to 0 in the site symbol.
Yes. These are symmetry elements, rotations, reflections, inversions that all intersect at a single common invariant point, which we usually place at the origin.
And the combination of these point symmetry elements is what defines the 32 crystallographic point groups.
A classic illustration of how these combine is the intersection of 2 mirror planes. If we have 2 mirror planes intersecting at an angle gamma between them, the combination of those 2 reflections is equivalent to a single rotation by 2 gamma around their line of intersection.
Which leads us to Euler's theorem. This is the fundamental geometric principle for combining rotations.
It is. The theorem states that the combination of any 2 rotations about intersecting axes can always be replaced by a single equivalent rotation about a third axis.
This seems simple, but it's the basis for proving which combinations of rotational axes are allowed to exist together to form a point group. The group has to be mathematically closed.
Meaning any combination of operations within the group must result in another operation that is already in the group.
So the ultimate synthesis of this chapter is answering the question, which combinations of our limited set of allowed axes 1, 2, 3, 4, 6 are actually compatible with the overall translational periodicity of the Bravais lattice?
You can't just stick a 4-fold and a 3-fold axis together and assume they'll work.
Right.
We rely on spherical trigonometry and Euler's theorem analysis to solve this. Imagine three intersecting rotation axes, A, B, and C. The angles between these axes are constrained by the rotation orders themselves. The set of equations derived from this provides the necessary relationships to test any combination.
And this calculation is what generated the monumental results shown in Table 8.2, which lists all the successful and unsuccessful combinations.
Let's walk through what that table reveals. It shows that many theoretically possible high symmetry combinations are instantly incompatible with the crystal lattice constraint. For instance, combining a four-fold axis with a six-fold axis, like 4, 6, 6, results in a no. The geometry just cannot close while maintaining the underlying periodic constraints.
But combinations like 2, 2, 2, 3 perpendicular 180-degree axes are compatible. This is the foundation of the orthorhombic system.
Exactly. The combination 2, 2, 4 is compatible, forming the tetragonal system, and 2, 3, 4 is compatible, forming the cubic system.
The combinations that are compatible are precisely those that form the basis of the 32 crystallographic point groups.
They are. These 32 groups are the result of the rotational freedom of point symmetry being severely restricted by the requirement that the resulting orientation must also fit the translational requirements of the Bravais lattice.
And most dramatically, this analysis reinforces what we discovered earlier about the five-fold axis. The table specifically confirms that the 2, 3, 5 combination, which generates icosahedral symmetry, the highest symmetry for a non-periodic object, is mathematically impossible in a repeating crystal lattice.
The cosine values resulting from the 2, 3, 5 combination fall outside the allowed range of -1 to +1. It means that the geometry of three such axes simply cannot intersect and remain compatible with a periodic structure.
So this analysis proves definitively why the translational requirement is the ultimate filter.
It limits the infinite possibilities of space down to a finite, perfect set of 32-point symmetries and their 230 space group expressions.
This has been a tremendously dense, but a critical deep dive into the very fabric of crystalline structure. We started with a simple definition of symmetry and moved quickly into the essential algebra.
The 3x3 rotation matrix and the fundamental necessity of the 4x4 site symbol using homogeneous coordinates to manage translation.
We established the absolute mathematical requirement for crystalline periodicity, which filtered all possible rotations down to just the 5 allowed orders, 1, 2, 3, 4, and 6.
Then we explored the complexity of combined operations, demonstrating how screw axes and glide planes generate the helical and layered structures that define specific space groups.
And finally, we saw how point symmetry operations, when tested against the compatibility demands of the Bravais lattice via Euler's theorem, ultimately restricted all possible combinations of rotation and reflection into the definitive 32 crystallographic point groups.
Our entire journey today has been focused on why certain symmetries are allowed in crystalline solids. But I encourage you to use this knowledge as a springboard.
A final thought.
Yes. If the five-fold axis is mathematically forbidden in periodic crystals, how is it that we have discovered quasicrystals, materials that exhibit five-fold symmetry without strict infinite periodicity? Mull over how nature achieves this ordered yet non-repeating structure, defying the most fundamental constraint we discussed today. That's your assignment for further exploration into the beauty of imperfection.
That is a fascinating, provocative thought to end on. For the learner, this was your complete deep dive summary of the fundamental concepts of crystallographic symmetry. We hope this knowledge helps you appreciate the mathematical constraints that govern the silent, stern perfection in the microscopic world around you. We'll catch you next time.